In this work, I'm going to talk about perception program. This work was accepted in CVPR 2026. Despite advancements in multimodal large language models, many vision problems are still highly benefited by relying on external tools, such as this one, where you get two views of the same image and you have to find matching points. This problem, where you are given two camera views and you have to infer where the camera is moving, or this problem where the MLM is given a depth map and is tasked with reconstructing the information that it was given. We studied this in our paper and we see that the prediction gets severely degraded with respect to what it should have looked like. The existing visual tool calling approaches for the problems presented can be roughly classified in either program synthesis, where the model synthesizes a script to compose visual tools, for example, drawing circles or drawing lines, and also chain of thought approaches, where the model emits tokens that carry visual information directly in the chain of thoughts, such as a depth value. The issues with the existing approaches are reliance on training and data collection, which make it expensive when trying to extend to new settings, increased latency when composing multiple tool calls, and also the fact that reasoning with pixels is harder than with text. In the paper, we ask this question: what if instead of relying on the model to figure out what the pixels mean, we explain it to it in a structured textual format? In perception programs, we do exactly that. In a standard VQA setting, the model gets a query and an input pair. In a tool augmented setting, it gets a query, an input pair, and a tool, often in visual format. And in our perception program, we take this tool and we pre-process it before feeding to the model. The LLM gets textual description. For example, here, one example, it gets two frames, and then it has to reason about where the camera is moving. So for this task, we pass the two frames for a tool that get an optical flow, and from the perception program generator, we can get this YAML explaining structured format what is in this image, and then the LLM can use that to solve its downstream task. In the paper, we consider the following six blink tasks. The results are that using the perception program significantly improves the state of the art on all of them. We can see here the vertical line is the state of the art. The this topmost methods are the existing competing approaches, and these bottom ones are the ones that use PP. And this is an average across tests. We see that it works across architectures, from commercial models such as GPT-5 Mini and Gemini Pro to even Intervia with 2 billion parameters only. And we also show in the paper that plugging perception program directly in competing methods is enough to improve them gravely, such as in the visual sketchpad method here in this table. We also have some analysis in the paper showing that when the model is asked to do the tool to perception program conversion itself, it degrades the information. We show that here on the relative depth estimation problem by showing that the candle tau between the ground truth and the reconstruction degrades as resolution increases. And we also show for the visual correspondence problem by plotting the error versus displacement. And this line here means that the model is simply copying the input that it was given. We further show on these bar plots that if the model tries to use these reconstructions to solve the problem, it does not perform nearly as well as the real perception program. The conclusion is that interpretation of pixel level information in tool call pipelines hinders the ability of the model to reason if we instead structure it and parse it as it as text. This is a simple and training-free technique that significantly enhances this capability across a wide range of model sizes. Thank you.